Hello, my name is Michael Rothman, and today I'm going to be discussing my research on biosignature detection in exoplanetary atmospheres using Monte Carlo simulations. And my research here at Ohio State University is done under the advisement of Anil K. Pradhan and Sultana N. Nahar. We are in an extremely exciting time in the history of astronomy. With over 4,300 exoplanets now discovered and confirmed by missions such as the Kepler Space Telescope, the Spitzer Space Telescope, and TESS, we're now witnessing the natural step from discovery to categorization and characterization. The detection of an atmospheric biosignature on another exoplanet would be a novel discovery, and we're closer than ever to doing so. Upcoming missions like the James Webb Space Telescope, seen there on the left, which is hopefully scheduled to launch late this fall, and the ELT are poised to do just this. Publications such as Swain et al. And Barclay et al. Have already reported preliminary results of atmospheres on rocky exoplanets and may be good candidates for future missions to study in closer detail. If we hope to find biosignatures in exoplanet atmospheres of rocky exoplanets, and furthermore find life at all, we must first look closer to home here on Earth. All known DNA-based life resides here on Earth, and thankfully this life has created a vast and complex biosphere for itself, which contains thousands of biosignatures. Detection and characterization of spectral features of these biosignatures in Earth's atmosphere allows us to characterize biosignature abundances on other rocky exoplanet atmospheres. Now, in order to characterize these biosignature abundances, we're developing GN4 exoplanets, or GN4 EXOP. And GN4 EXOP is based on GN4, a multi-purpose Monte Carlo program package allowing for the modeling of transmission of radiation and particles through matter. GN4 EXOP will provide a toolkit to precisely and accurately model both differentiated atmospheric radiation transport on the macroscopic level and atomic radiative transitions on the microscopic level. It does this by simulating passage of stellar radiation fields through exoplanet atmospheres, generating absorption and emission spectra, which are analyzed and abundances characterized. As I said, GN4 EXOP is based on GN4, which uses the Monte Carlo method as the foundation of its event processes. Generally, the Monte Carlo method relies on repeated random sampling to obtain numerical results for potentially deterministic problems. GN4 accomplishes this by using random number generators. The Monte Carlo method in GN4 EXOP's case will approximate the probabilistic nature of light particle interactions in our simulations. Photoexcitations, de-excitations, photoionization, as well as other spectral information all utilize this method. Of course, these effects are encapsulated and dictated by opacity and density profiles of materials in GN4 EXOP, which are well defined in its libraries. The simulations ran by GN4 EXOP will model radiation field propagation through multi-layer atmospheric phantoms. And by phantoms, we mean a material which is relatively transparent and that photons can interact with, such as an exoplanet atmosphere. Now, GN4 EXOP is a highly modularized toolkit, the operation flowchart of which can be seen on the left. In principle, we're importing stellar radiation fields, simulating passage and interaction of the radiation field through a defined planetary atmosphere, and collecting the resulting radiation field to capture generated absorption and emission spectra of the system. The planetary atmospheres will have specified layering, each having its own density, temperature, and composition. These atmospheric material layers are composed of atoms, ions, and molecules, which are compiled into a database within the toolkit. Once the simulation is complete, we determine the line abundances from the spectra. From here on, I will be following the sequence of the flowchart and discussing topics as they're handled by GN4 EXOP. Now, the primary candidates for study by our group are G, K, and M dwarfs. Now, our first test case will be everyone's favorite G25 star, the Sun. The Sun's irradiance and flux residual spectra are first imported into GN4. Outputting these after filtering through GN4XOP, we plot them in MATLAB, which you'll see in the next couple slides. For the full test case, we will import solar spectra along with the Earth's atmospheric composition, layer densities, and temperatures. Once obtaining the generated absorption and emission spectra out of GN4XOP, we will compare these results with the observations to ensure accuracy and precision. You can see in the top right here, the solar irradiance spectrum, or the energy outputted by the sun that's incident on the Earth's atmosphere. And the bottom right is the solar flux residual, or the energy as it's received on Earth's surface after filtering through Earth's atmosphere. We can see that GN4XOP handles both of these cases with the expected results. For example, in the solar radiation spectrum, you can see that it peaks at about 450 nanometers in yellow. We can see that this data is quite busy, and so we smooth the data using a Gaussian convolution, which cleans up the noise. So what does it look like? You can see here on the screen this new spectra, which has a resolution of 1 nanometer, similar to observations. You can also see key features such as the H alpha and beta lines, as well as the calcium infrared triplet. Now, we can also look at the smooth residual spectrum, and you'll see that these same key features are translated between them, as we expect. The spectrum has also a resolution of 1 nanometer, and this plot is cleaned up significantly. Outside of the key features from the irradiance spectrum, we can also observe, for example, key water bands in the infrared, which are wavelength ranges where water absorbs a significant portion of the irradiance. Now, we talked a lot about the simulated atmospheric phantom, but how is it created and what does it look like? Now, this is a multi-layer phantom with each layer representing a different atmospheric layer. You can see here on the left-hand side the atmospheric layering of the Earth's atmosphere. Now, each layer is composed of its own material in GN4XOP. For example, the material of the stratosphere would be composed of 78% nitrogen, 21% oxygen, 0.9% argon, and the remaining 0.1% would be a mixture of other constituents such as water, ozone, carbon dioxide. In contrast, however, the ionosphere will be containing mostly ionic nitrogen, oxygen, and helium. Now let's step from atmosphere building to system geometry. We see on the right a diagram of the system geometry. And the imported radiation field, shown as a large number of arrows here, are launched through a galactic medium composed of hydrogen. The photons are incident upon the multi-layered phantom, passing through the atmosphere and interacting with it. This is the most important part, as the absorption spectra are generated in this step. Now we place the detector far from the star in the system to simulate the observation of what would be a transiting exoplanet. We collect the absorption and emission spectra here at the detector, similar to how we would observationally on Earth. Let's transition again from the macroscopic interactions now to the microscopic. And there are three main processes for photoabsorption. We have bound-bound, bound-free, and free-free, also called inverse Bremsstrahlung. There's also photoelectron scattering, such as Thomson and Rayleigh scattering, but GN4XOP will focus mainly on bound-bound and bound-free interactions. We will use these to model radiative transfer through the multi-layer phantom using the radiative transfer equation. Our key quantity in this equation is the monochromatic capacity, kappa nu, which is hidden within the optical depth. Our bound-bound transitions are excitation and de-excitations of electrons bound to an atom, which occur when a sufficiently energetic photon is incident upon the atom, and this excites the electron from one atomic level to another. Photoexcitation is governed by the transition probability as well as the absorption oscillator strength. Our newly excited electron will decay at a spontaneous decay rate, or A value, with the lifetime of our transition being the inverse of this rate. Our line oscillator strength is also related to our absorption cross-section. This cross-section, as well as the bound-bound monochromatic capacity, depend on the line profile factor, which distributes the line oscillator strength over a given frequency range. This profile factor is determined according to the environment via the line broadening mechanisms such as temperature and pressure. Now, bound-free transitions, also called photoionization, occur when a photon with an energy equal to or greater than the ionization energy of the electron is absorbed. The electron is thus ionized and carries away the energy in excess of the ionization energy. Now, as before, we define our photoionization cross-section and monochromatic capacities, where now the line strength is dependent on the initial bound state wave function and the free electron wave function at continuum energy epsilon. Now we can see on the left-hand side examples of these bound-bound transitions. In the star Procyon corona, we can see observed helium-like oxygen spectral lines, which are plotted on that top frame. This is an example of X-ray lines whose line ratios yield accurate temperature and density diagnostics, the data for which is used observationally to calibrate instruments. In the bottom, we can see predicted diagnostic lines, W, X, Y, and Z, for helium-like phosphorus, which are not broadened as we do not include the temperature and pressure as we did in the top frame as broadening mechanisms. Now, to calculate these predicted diagnostic lines of phosphorus-14, we use the code SUPERSTRUCTURE. This is hosted by the Ohio Supercomputer Center. We can use SUPERSTRUCTURE to calculate predicted transition probabilities, energies, and A values, among other important spectral information. The primary focus is on biosignature elements, hydrogen, carbon, oxygen, nitrogen, phosphorus, and sulfur. We've already calculated values for all phosphorus ions, the results for which are in preparation for publication. Now, phosphorus is vital as it is the backbone of DNA. So if we hope to find life which at all resembles life on Earth, we must find star systems with abundances of phosphorus. The monochromatic capacities we've just defined are integral to the operation of GN4XO. Now, these terms contain all the absorption information for the atom, ions, and electronic transitions for molecules. We will calculate these profiles for numerous atoms, ions, and molecules, storing them in GN4XO for simulation use. This database will be one of the end products of the monochromatic opacity profile module, which is currently under development. When calculating these, we isolate the absorption features for use in generating absorption and emission spectra. Now, on the left are the preliminary results of an isolated water absorption feature located from about 2.5 to 4.5 microns. We see that the oscillator strength features are present as expected based on the results seen on the right, which are observations of water absorption in the atmosphere of a hot Jupiter. And we intend to build the monochromatic opacity database for as many biosignatures as literature data and, frankly, time allows. Now, for this molecular data, we rely on other research groups like our collaborators, Dr. Jonathan Tennyson and the ExoMol group. Despite rigorous research on molecular spectral information, there are only a handful of spectra that are considered to be highly comprehensive, such as water. There are over 16,000 biosignature molecules which can be considered of interest for exoplanetary atmospheric research. GN4XOP will first be equipped with spectral information of dominant molecules such as carbon dioxide, nitrous oxide, methane. The primary focus is on molecules which are both well-defined in literature, so that we have a wealth of spectral information, but also biosignatures that are produced mainly through biological and not abiotic processes. Now, GN4XOP will enable us to characterize biosignature line abundances in exoplanetary atmospheres by utilizing Monte Carlo simulations. As a first test case of GN4XOP, we filtered the solar irradiance and flux residual spectrum through GN4XOP. As a full test case, we will model Earth's atmosphere as a multi-layer phantom and propagate the solar radiation field through it, obtaining the emission and absorption spectra on the other side. Once this test case is fully realized, we move on to other stellar systems hosting rocky exoplanets in search of biosignatures. As for right now, we're currently developing the monochromatic capacity profile module. Now, this is a huge step in development, and this will enable us to have the beginnings of a spectral information database within GN4XOP for simulation use. And we utilize the code SUPERSTRUCTURE for atomic and ionic spectral information. And we're gathering molecular species data from ExoMol for molecular spectral information. I developed a code to transform transition information provided by ExoMol into usable oscillator strengths, lists of these for calculations by GN4XOP and monochromatic capacity generation. So thank you to everyone here for listening to my talk, and thank you for to the conference for allowing me to speak here. And finally, thank you to the Ohio State University, as well as my advisors, Dr. Anil Pradhan and Dr. Sultana N.A.R. I'm happy to take any questions at this time. Thank you.